Welcome to the Unit 8 test or the Unit 8 study guide on energy. The other half of this is linked in the video description. That is the other half on matter. To begin, we are going to fill out this table for endo and exothermic. Beginning with endothermic reactions, their delta H is going to have a positive value. The reaction is going to feel cold because it is busy absorbing a bunch of energy. The direction of heat flow, endothermic, heat is going to enter the reaction, and the work is done on the reaction, meaning that energy is added to that reaction. Exothermic reactions are the opposite. They have a negative delta H value. The reaction is going to feel hot because lots of energy is exiting the reaction, and that's what you'll be able to feel. And then finally, the work is done by the reaction because it is releasing a bunch of energy. Up next, what are the 6 phase changes? And you are asked to categorize them as either endo or exothermic. There are 3 endothermic phase changes, and that is melting, vaporization, and sublimation. That is where energy is going to enter the system. And then your exothermic reactions is where heat is removed from the system. That will be freezing, condensing, and deposition. Now we have some math problems. How much heat energy is required to melt 250 grams of ice? And how much heat energy is required to boil 250 grams of water? For each of these problems, you will have to use a Q equation. Remember, Q is heat measured in joules. For melting, we would use the equation Q equals mHF. HF is the heat of fusion. That little f is just describing the type of heat. So our mass, M, is 250 grams, and we would multiply that by the constant, the heat of fusion for water, which is 334 joules per gram. Multiply that out, and we would be left with 83,500 joules, or 83.5 kilojoules. For boiling, we would use Q equals mHV, HV being the heat of vaporization. Again, we take that mass of 250 and multiply it by the heat of vaporization, which is 2,260 joules per gram, with a final heat value of 565,000 joules or 565 kilojoules. My favorite question, why does it take more energy to boil this sample than it would take to melt it? The reason comes down to potential energy. It takes more potential energy to pull the particles apart from each other when we are boiling from a liquid to a gas. Those particles have to spread out far more, so you need a lot more energy for that to happen than you would need for melting, where your particles are going from solid to liquid and only just separating a tiny bit. So for that reason, boiling will take more energy. Up next, you are asked to label the phase diagram, including phase changes, phase of matter, and the triple point, and then you are asked to define the triple point. The general format for a phase diagram is this Y shape, although some of them are going to be longer or skinnier. It's going to depend on the particular substance, but they will generally have this Y shape. This section up here under higher pressure and lower temperature is going to be solid, and these lines represent phase changes. So as you cross this line from solid to liquid, you would be melting your sample. The area between the Y is going to be liquid. You're at a higher temperature, but a little bit of a higher pressure, holding your particles together a little bit. And if you cross that line to the left, you would be freezing your sample. Across the bottom, where you have any type of temperature but is decently low pressure, you are going to have a gas, and that gas, when you apply more pressure, is going to condense into a liquid. If you were at that liquid and reduce the pressure, you would be left with a gas because you have vaporized the sample. This line back here between solid and gas is going to represent sublimation, going south, I guess, decreasing the pressure, and increasing the pressure, you are going to have a deposition. The triple point is going to have the perfect conditions for all phases of matter to exist at the same time. So this is marked by this purple dot right here. That is where solid, liquid, and gas can all coexist under the perfect conditions of temperature and pressure. Next up is specific heat capacity. The first is to define specific heat capacity, and then next is to determine the amount of heat energy required to raise the temperature of 250 grams of water from 20 to 40 degrees Celsius. I like to define specific heat capacity as the ability of a substance to hold on to heat. The higher specific heat capacity, the better it holds on to heat. In order to solve this math problem, we would use the equation Q equals mc delta T. We have no phase change, but we do have a temperature change marked by delta T. M stands for mass in grams. C is the specific heat capacity of water, which is 4.18 joules per gram Kelvin or joules per gram Celsius. And delta T is going to be the final temperature minus the initial temperature, so 40 minus 20. In total, that will give us a temperature change of 20. Multiplying all of those values, we wind up with 20,900 joules or 20.9 kilojoules. Calorimetry, remember, is just the lab process of putting all of those Q equations to work. We have a 15-gram block of copper at 22 Celsius, and it's added to a 100-gram sample of boiling water, which means it's at 100 Celsius. How much heat energy did the copper block gain? The specific heat of copper is 0.385 joules per gram Celsius. Because we're looking at a change in temperature and not a change in phase, we would use the equation Q equals mc delta T. So for this, our mass is 15 grams. The specific heat of copper was given in the question, and then our temperature ended at 100 but began at 22, so you would subtract those two values to determine the change in temperature. Multiply that all across and you would get 450.45 joules of heat added or gained by the copper. Assuming that the water sample is having no new heat added to it, as in it's been removed from the Bunsen burner or from the hot plate, what is the new temperature of the water after it lost energy to the copper? In order to do that, you would still use the equation Q equals mc delta T, but at this point you would calculate the delta T value. Q should be the amount of heat that the copper had lost, or rather the copper had gained, because the water gave all of that energy to the copper. So we would plug in that 450.45 for the total Q of the water. The mass of the water is 100 grams and the specific heat is at 4.18. Again, we're solving for delta T, which comes out to 1.077 Celsius. So if we know that the water is losing energy, that means that its temperature should be dropping. So we're going to subtract that 1.077, and that leaves us with 98.92 Celsius. That is a very small change in temperature, but this is because we had a very small block of copper with a very low specific heat, so it heated up very quickly. The next question is on heating and cooling curves. So you are asked to label this heating curve with the phases of matter, equation used, boiling point, melting point, and type of heat flow. On a heating curve, we are adding energy to the system, so this system would be endothermic, traveling up the graph in this direction. The slanted parts of the graph represent your phases of matter. So here we have the heating of a solid, the heating of a liquid, and the heating of a gas. In order to use heat equations there, the only heat equation you could use is Q equals mc delta T, because we have a change in temperature, not a change in phase. The flat parts of the graph represent phase changes, and because we are endothermically changing, adding energy here, we have the melting between solid and liquid, and for that we would use Q equals mHF. For water, this would be 0 degrees Celsius. On this side over here, we have vaporization, and vaporization is going to use the equation Q equals mHV because we're converting from a liquid to a gas. If this is water, that would be 100 degrees Celsius. Next up, you are asked to do the same thing, but for a cooling curve. Traveling across the graph from left to right, we have our exothermic phase changes, meaning that we are losing heat as we go across this graph. Again, the slanted parts represent the phases of matter, gas, liquid, and solid, and they are losing heat as we go through, so their temperature is dropping, which would indicate we use the equation Q equals mc delta T. The flat parts of the graph, again, are phase changes. Up here, we have condensation between gas and liquid, and for that, we would use Q equals mHV. Between liquid and solid, of course, we have freezing, and for that we would use the equation Q equals mHF. If this sample were water, condensation would happen at 100 degrees Celsius, and freezing would occur at 0 degrees Celsius. That is everything on energy. Again, the link for the matter video will be in the description below the video. If you have any questions, please leave them in the comment section below the video. Subscribe so you don't miss the next unit. We will be discussing gases. I can't wait to see you there. Bye.